Welcome to the third lecture on trigonometric functions. In the last lecture, we ended up with deriving an expression for cos of x minus y and cos of x plus y in terms of cos x, cos y, sin x and sin y. So, we will continue with that, and in this lecture we are going to derive expressions for sin 2x, sin 3x, cos 2x, cos 3x in terms of sin x, cos x and some other derivations also. So, towards the end in the last lecture we proved that cos of x minus y is equal to cos x cos y plus sin x sin y, and then by substituting replacing this y here with minus y, we got the other expression that cos x plus y is equal to cos x cos y minus sin x sin y. So, this can be used, these two formulas can be used to find the cosine of some other angle apart from the well known angles. For example, we already know the cosine and sine for 45 degree and 30 degrees. So, that can be used to find the cosine of 15 degrees by using this formula and having x equal to 45 degree and y equal to 30 degrees. So, that is written here. So, cos 45 minus 30, and then of course, I use this formula here. So, what we get is cos x, which is cos 45 cos y plus sin 45 here sin 30. So, these are all degrees, okay, and this of course is equal to cos 45 is equal to 1 by root 2 and cos 30 is equal to root of 3 over 2. Sin 45 is also 1 over root 2 and sin 30 is half. So, you get, so that is how you get cos of 15 degrees is equal to 1 plus square root of 3 over 2 times root 2. Now, using these two basic formulas for cos x minus y and cos x plus y, other simplifications can also be derived. For example, here if we are given an expression of this type 2 cos x cos y, then it can be written as, so let us focus on these two equations here. So, if we add up these two equations, on the left hand side we are going to get cos x minus y plus cos x plus y, and on the right hand side sin x sin y is going to cancel because there is a plus here, there is a minus here, and then these two will get added up and we get 2 cos x cos y, and therefore 2 cos x cos y is equal to cos of x minus y plus cos of x plus y. And similarly, if we compute cos x minus y minus cos x plus y, then this term in both these equations will get cancelled and we will get 2 sin x sin y. So, 2 sin x sin y is equal to cos x minus y minus cos x plus y. So, later on when we do a lot of examples, you will see that this kind of this type of formulas will be very handy and it will be good if you can memorize it. So, we saw in the previous slide as to how we can compute cos of 15 degrees. Somebody might think that now that we have computed cos 15 degrees, can we compute cos of half of 15 degrees, which is cos of 7.5 degrees, and yes, it is possible. So, to do that, let us first derive an expression for cosine of 2x in terms of cosine of x, and then what we will do is we will put x equal to 15 degrees, half of 15 degrees, and then we will see that we can solve and find out cos of 7.5 degrees. So, now cos of 2x can be written as cos of x plus x, and then we use the formula on the previous slide for cos of x plus y, but with y equal to x. So, when you put y equal to x in this equation, you get cos x into cos x minus sin x into sin x. So, that becomes cos square x minus sin square x. But we know that sin square x plus cos square x is equal to 1 for all x, and therefore, in this equation we can replace sin square x by 1 minus cos square x, and that is the expression that we get. So, we now see that cos of 2x is equal to 2 times square of cosine of x minus 1. So, if you happen to know the value of cosine of x, you can compute the value of cosine of 2x. And in fact, you can show that this is also equal to 1 minus 2 times sin square x. To get that is very simple. You just need to go 2 steps back, and in this equation over here, you need to replace this cos square x term by 1 minus sin square x, and that is how you get this term here, this expression. Now, let us see how we can calculate cos 7.5 degrees, given that we know the value of cos 15 degrees from the previous slide. Before that, this equation can also be written in another way. So, we can write 2 cos square x is equal to 1 plus cos 2x, and therefore, cos x is equal to the ambiguity about plus and minus will depend on the value of x. Now, let us try and compute the value of cos of x for x equal to 7.5. So, we put x equal to 7.5 in this equation here. But we know that cos of 7.5 degrees is a positive number, a positive real number, and therefore, we are going to only take the positive square root. So, this is the value of cos of 7.5 degrees. So, it's very simple. On the right hand side, we just need to take the value of cos 15 degrees that we had calculated in the previous slide and substitute it here, and then compute the square root of this expression. Using the cos x minus y formula, many other simplifications can be done. For example, we will try to see what cos of x minus pi by 2 is. So, this is cos x cos y. So, here your y is equal to pi by 2, 90 degrees, plus sin x sin y. We know that cos of pi by 2 is 0 and sin of pi by 2 is equal to 1, and therefore, the first term here in this summation will be 0, and only the second term is going to contribute. So, this is equal to sin of x. Similarly, cos of x plus pi by 2 is, so we will use now the formula for cos of x plus y, with y equal to pi by 2, which is cos x cos y minus sin x sin y. Again here, because cos of pi by 2 is 0, this first term is equal to 0, and so what we get is minus sin x. Similarly, we can compute expressions for sin of y plus pi by 2 and sin of y minus pi by 2, but you would be probably wondering that we have not covered the expressions for sin of x plus y and sin of x minus y, but that is something that we will be doing in the next few slides. But here, even without that, we should be able to compute sin of y plus pi by 2. If you go back to this equation here, where we had written that cos of x minus pi by 2 is sin of x. Now, if we replace this x over here, so we say that x is actually equal to y plus pi by 2, then what we get is sin of y plus pi by 2, which is this, is equal to this expression, but with x equal to y plus pi by 2. So, we are using this substitution here. Therefore, sin of y plus pi by 2 is equal to cos of, instead of x we put y plus pi by 2 and then minus pi by 2 here. So, it is simply cos of y. Similarly, we can find out what sin of y minus pi by 2 is. We go back to this equation that we had just derived now, cos of x plus pi by 2 is equal to minus sin x. So, here what we do is we try to do the substitution x equal to y minus pi by 2. So, what we get then is that minus of sin y minus pi by 2 is equal to cos. Now, instead of x we have to put y minus pi by 2. So, we get, and there is a plus pi by 2 here, but there is a minus sign here, and since we do not have a minus sign here, we need to put a minus sign over here. So, this becomes equal to minus cosine of y. So, these four identities are very useful, and we will see that when we do some example problems later on. In this slide, we are now going to derive, similar to this expression for cos of x minus y equal to cos y plus sin x sin y. I am going to derive an expression for sin of x minus y in terms of cos x, cos y, sin x and sin y. And for that, we will use the result on the previous page, where we had shown that sin of, for any angle z, sin of z equals, if you, so sin of x equals cosine of x minus pi by 2. So, sin of z is cosine of z minus pi by 2. Cosine of z minus pi by 2. And here we will treat this as equal to z. So, by using this identity, what we get is that sin of z is cos of z minus pi by 2, but z is x minus y. So, this is cosine of z minus pi by 2. Which I can write as cosine of x minus y plus pi by 2. So, now if you see, this expression here is of the form cos of a minus b or cos of x minus y, where I will be treating this as the new y. And then we use this formula. So, we get this to be equal to cos x cos new y. So, this is the new y. So, cos x cos y, cos x cos new y, and then plus sin x times sin of new y. Now, from the previous slide we know that cos of y plus 2, cos of y plus pi by 2, cos of y plus pi by 2 is minus sin y. So, I am just going to replace this x over here with y. So, this term here becomes cos x, and then there is a minus sin y. Plus sin x, and then again from the previous slide we had derived that sin of y plus pi by 2 is the same as cos of y. So, using that we have sin of y plus pi by 2. And that is the final expression, which is that sin of x minus y is equal to sin x cos y minus cos x sin y. Using this formula, we can now easily derive the expression for sin of x plus y. We just need to replace this y with minus y. For sin x plus y, we write this as sin of x minus y. So, this minus y is like the y that we had in the expression for sin of x minus y. From the previous slide, we know that sin of x minus y is sin x cos y minus cos x sin y, and therefore, here just replacing this y with minus y, we will get sin of x plus y equal to sin x cos of minus y minus cos x sin of minus y. Now, we know that cosine is an even function and sine is an odd function. Therefore, cosine of minus y is cos y and sine of minus y is minus sin y. So, using these two facts, we further get that sin x plus y is finally equal to sin x cos y plus cos x sin y. So, now we have also derived the expressions for the sine of sum and difference of two angles, which is what we did in the previous couple of slides, and I have summarized the two equations over here. Now, if we add these two equations, this term here and this term here will get cancelled out and we will get twice of this term, and therefore, 2 times sin x cos y is equal to sin x plus y plus sin x minus y. In a similar manner, if we compute sin x plus y minus sin x minus y, then these two terms will get cancelled out and we will get twice of cos x sin y. Therefore, two cos x sin y equals sin x plus y minus sin x minus y. We will now see how to compute the sine of double of an angle if we simply know the sine and cosine of this angle x. It is very simple. We go back to the expression for sin x plus y and we replace this y with x. So, we get sin 2x is sine of x plus x. Now, in this formula we have y equal to x. So, y equal to x here and y equal to x here. So, we get sin x cos x plus cos x sin x, which is equal to 2 times sin x cos x. Earlier we had seen how to find the cosine of the half of some angle. So, we saw how to compute the cosine of 15 by 2 degrees when we just knew the value of only cosine of 15 degrees. So, similarly we will show you how to compute the sine of the half of some angle x. So, we start with this formula cos 2x equals to 1 minus 2 sin square x, which we have already derived on one of the previous slides. So, from here by doing manipulation what we get is sin square x is 1 minus cos 2x over 2, and therefore, sin x is equal to plus minus root of 1 minus cos 2x over 2. So, again here the choice of plus and minus will depend on the value of x. So, for example, if we were to find out sine of 7.5 degrees, using this formula here we get sine of 7.5 degrees is equal to, now we know that sine of 7.5 degrees is a positive real number and therefore, we only take the positive sign here. So, it is equal to square root of 1 minus cos of 15 degrees over 2, and this we can compute since we already know the value of cosine of 15 degrees. We already know this equation that cos of x plus y plus cos of x minus y is 2 cos x cos y. Now, suppose that x is actually equal to the sum of the half of the sum of two different angles and y is the half of sum of half of the difference of these two same angles a and b. So, if we substitute x with a plus b by 2 and y with a minus b by 2 in this equation, what we end up getting is that 2 cos a plus b by 2 into cos a minus b by 2 equals, now cos x plus y, but x plus y is a plus b over 2 plus a minus b over 2, which is a. So, we get cos a, and similarly x minus y is b. So, cos of x minus y is cos of b. So, this formula actually gives you a way of converting sum of two cosines into product of two cosines of the sum and differences, half of the sum of sum and differences. So, for any angle a and b, cos a plus cos b, which is the sum of the cosine of the angles, is 2 times cosine of a plus b by 2 times cosine of a minus b by 2. And similarly, if we also remember, we had also derived that 2 sin x sin y equals cos of x minus y minus cos of x plus y. And again doing the same substitution here with x equal to a plus b by 2 and y equal to a minus b by 2, what we will end up getting here is 2 into sine of a plus b over 2 into sine of a minus b over 2 equals x minus y is equal to b. So, cosine of b minus x plus y is a, cosine of a. So, this formula again gives you a way of expressing the difference of the cosine of two angles as a product of the sine of the half of the sum and the difference of those two angles. Similarly, we know that sine of x plus y plus sine of x minus y is 2 sin x cos of y. And we do the same substitution here again with x equal to a plus b by 2 and y equal to a minus b by 2. So, what we get is 2 times sine of a plus b over 2 into cosine of a minus b over 2 equals x plus y is a. So, sine of a plus x minus y is b, x minus y is b. So, sine of x minus y will be sine of b. So, this is another expression for converting the sum of sines to product of sine and cosine. Similarly, we also know that sine of x plus y minus sine of x minus y equals, since sine of x plus y is sine x cos y plus cos x sin y. So, when we replace this with that expression and also the similar expression for sine of x plus x minus y, what we get is, so we can write it here, sine x plus y is sine x cos y plus cos x sin y, and sine x minus y is sine x cos y minus cos x sin y. So, if we subtract sine x minus y from sine x plus y, what we get is 2 times cos x sin y. So, this expression here, and again in this expression we can replace x with a plus b by 2 and y with a minus b by 2, and what we will end up getting is 2 times cosine of a plus b by 2 into sine of a minus b by 2 equals sine of a, because x plus y is a, minus sine of b. So, this gives you an expression for a way of converting the difference of the sine of two angles to again the product of sine and cosine. Now, let us see how to calculate the cosine and sine of thrice of an angle. So, cosine of 3x can be written as cosine of 2x plus x, but we know that cosine of a plus b is cosine of a cos of b minus sine a sine b. Now, using this formula here with a equal to 2x, so this a we will choose it to be 2x and b as equal to x, we will get cosine of 3x as cos 2x times cos x minus sine 2x times sine of x, which is equal to, now we know that cosine of 2x is equal to 2 times cos square x minus 1. So, we use that result which we had derived earlier. Times cos x minus, and we had also derived that sine of 2x is 2 times sin x cos x. So, that is what we are going to use for sin 2x here. Times sin x. Which is equal to minus 2 cosine of x. So, this is this particular term 2 times cosine x times sin square x, but sin square x is nothing but 1 minus cos square x. So, finally, we get two cos cube x minus cos x minus 2 cos x plus 2 cos cube x, which is equal to, so 2 cos cube x here and 2 here, so that becomes 4 cos cube x minus 3 cos x. So, that is cosine of. So, this formula helps you to, so if you know the value of cosine of x, you can very easily compute the value of cosine of 3 times x. Similarly, we now derive another expression to compute the sine of 3 times x, sine of 3x in terms of sine of x. So, again sine of 3x, we are going to use the formula sine of a plus b equals sine a cos b plus cos a sine b, and we are going to put a as 2x and b as x. So, when they get added up, we get sine of 3x. So, therefore, we get sine of 3x equals sine of a, but a is 2x. So, sine of 2x times cos of b, but b is x. So, cos of x plus cos of 2x times sine of x. We know that sine of 2x is 2 sin x cos x, and cosine of 2x is 1 minus 2 sin square x. So, we are going to use these two expressions here. So, this is the expression for sin 2x. So, we are going to multiply that with cos x plus cos 2x is 1 minus 2 sin square x. Therefore, two sin x times cos square x, but cos square x is 1 minus sin square x. And then we can open up this expression. So, it becomes sin x minus 2 sin cube x which, if you simplify further, it will be equal to 3 sin x minus 4 sin cube x. So, that is your sine of 3x. So, again, as you see, we can, if you just know the value of sine of x, you can find the value of sine of 3x. And of course, you can do vice versa also, because this is actually a, if you see this part is cubic in terms of sine x. So, if you know the value of sine of 3x, you can find sine of x by finding the roots of a cubic equation. Most of this lecture we have been talking, and also the previous lecture we have been talking about sine and cosine and giving expressions for sine of x plus y, sine of x minus y, cos of x plus y, cos of x minus y, and then sine of 2x, sine of 3x, cos of 2x, cos of 3x. But then we are going to introduce this other function called tangent of x, as you might already be knowing from your trigonometric ratios, but we introduce it here more formally now. So, again we consider a unit circle here of unit radius whose center is at O, this point O, and this is the horizontal axis is the x axis, the vertical axis is the y axis. And suppose we have this point P on the circle here, and whose coordinates are a, the x coordinate is a and the y coordinate is b. So, this is a and this is b, and therefore, the tangent of the angle of rotation, because if you see this OP radius is initially here, it is initially at OB. So, the ray, we initially have a ray OB here, and for B to reach this point P, we have to rotate this ray around this center O by an angle of x. So, the amount of rotation is x, and therefore, this tangent, now if you look at this right angle triangle here, because this is a perpendicular. So, if you look at the right angle triangle here, the tangent of this angle is equal to the value of the opposite, the length of the opposite side. So, the opposite side to this angle x is this side, whose length is equal to b. So, b upon the length of the adjacent side. So, the adjacent side to this angle x is this side OA, whose length is a. So, tan x is b upon a. And if you try to see further in probably lecture 1 or yes, lecture 1, we had defined sine of x as the opposite side, the length of the opposite side divided by the length of the hypotenuse. But since this is a unit circle, this hypotenuse is actually a radius of unit length, and therefore sin x was simply equal to the y coordinate of this point P, and cosine of x was equal to the length of the adjacent side of this right angle triangle, which is nothing but the x coordinate of this point P, which is A. And then we immediately realize that b by A is nothing but sin x divided by cosine of x, and therefore we get the relation that for any angle x, the tangent of x is equal to sin x upon cosine of x. Let us try to now plot the graph of tan x on the y axis versus x on the horizontal axis here. And for us to do that, we will take help of again this unit circle here with center at O. So, let us say that we start with the angle of rotation x to be equal to 0 degrees. So, we are somewhere here at 0 degrees. So, when x is at 0 degrees, we are actually somewhere at this point. So, because there is no rotation, so this OP is actually over here, and the coordinate of this point is 1, 0, and therefore, since tan x is equal to the ratio of the y coordinate to the length of the y coordinate of this point to the value of the x coordinate. So, when x is equal to 0, we are here, and then if you see this ratio is simply equal to 0, because at this point the y coordinate is 0. So, therefore, at x equal to 0, tan of x is 0. So, this is where we are on the graph at x equal to 0. And then as we increase x, so what that means is that this ray we try to rotate in the anti-clockwise direction. So, that is going to increase the value of x. So, when we increase the value of x, what starts to happen is that the y coordinate, which was initially 0, will start taking positive values. For example, at x equal to 45 degree, we have a right isosceles triangle here, for which both the y coordinate and the x coordinate will be equal, right. And therefore, when x is equal to 45 degrees, tan of x will be equal to 1, because both the coordinates are 1 upon root 2. So, that point is somewhere here. So, when x equal to pi by 4, so let us say this is 1. So, the value of tan x will increase from 0 to 1, like that. And then when x increases further, what happens is that the value of the, so for example, when the ray rotates further in the anti-clockwise direction, and suppose the ray is over here now, so the angle now is more than, let us say, so suppose if this was 45 degrees, the angle is now more than 45 degrees. So, maybe we are somewhere close to pi by 2. So, as the angle moves closer to pi by 2, what happens is that the x coordinate of the point starts to reduce and it becomes very close to 0. So, essentially the A goes to 0. So, as A goes to 0, but the y coordinate is still close to 1. So, it will be somewhere approximately 1 as you go closer to pi by 2. So, since this will be finite, but this will go to 0, the tangent of this angle x as x goes nearer and nearer to pi by 2 will start going to infinity, because 1 by 0. So, this is how it will go. So, it will go to infinity. And similarly, we can draw the same thing for the negative side. So, if you start from here and if you go in the clockwise direction. So, now we are reduced. So, as we know, going in the clockwise direction will give you negative values of this rotation angle. So, this is the, so for example, when we are here, this angle is, let us say, minus 45. So, that corresponds to x equal to minus pi by 4 on this graph. But when we are on this side, the x coordinate of any point, let us say in this fourth quadrant, the x coordinate is still, the x coordinate A will still be positive, but the y coordinate is going to become negative. And therefore, in this quadrant here, the value of tangent of x will be negative. And if you try it, for example, if this angle is 45 degree, then what we will see is that tan of minus 45 will be equal to minus 1, because the, if you see this point Q here, the coordinates of this point will be, the x coordinate will be 1 by root 2, but the y coordinate will be minus 1 by root 2, because it is on in the fourth quadrant, minus 1 by root 2. So, when you take the ratio of minus 1 by root 2 divided by 1 by root 2, you get minus 1, which is, let us say, somewhere here, this is minus 1. So, somewhere here. And then similarly, when we go to from minus pi by 4 further clockwise towards minus pi by 2, again what happens is that the x coordinate goes to 0, but since the value of the y coordinate is negative, this ratio will go to minus infinity, like this. And in a similar manner, this whole graph can be filled up by continuing to rotate further beyond pi by 2. This graph can be completed. So, compared to sin x and cos x, see, sin x and cos x were bounded functions. What I mean by bounded is that for any x, the value of sin x was always between minus 1 and plus 1, and the value of cos x was also between minus 1 and plus 1. But that is not so with tangent of x. The value can really go unbounded. So, essentially for x, the angle x, when it is actually the equal to odd multiples of pi by 2, what, because if you see, this is nothing but tan x is nothing but sin x by cosine of x. So, it is very much clear that tan of x will be unbounded for all those x for which cosine of x goes to 0. And we know that cosine of x goes to 0 only when x is an odd multiple of pi by 2. So, whenever x is an odd multiple of pi by 2, tan x will be unbounded. It will be minus infinity or plus infinity. So, just as we had computed sine of minus x and cos of minus x, we can also calculate tan of minus x. But since tan of x is sin x by cos x, tan of minus x will be equal to sine of minus x divided by cosine of minus x. I mean, we can just treat this as some other variable y, and then tan of y is sine of y divided by cos of y. But we know that sine of minus x is, since sine is an odd function, this is equal to minus sin x, and cosine of minus x is, because cos is an even function, it is equal to cosine of x. But then sin x upon cos x is tan of x. So, this is equal to minus tan of x. So, what we see is that tan of x is actually an odd function, because tan of minus x is minus of tan x. We can find sine of x plus pi, again taking this as y, tan of y is sin y by cos y. So, it is sine of x plus pi by cos of x plus pi. Now, sine of x plus pi is equal to, and you can again use this formula for sine of x plus y. So, it will be sine x into cos y plus cos x into sine y. So, this is sine of x plus pi divided by cos of x plus y is cos x cos y minus sin x sin y. Now, we know that sine of pi is 0, therefore, this term will go to 0, and even here this term will go to 0 because sine of pi is 0. So, what remains is sin x cos pi divided by cos x cos pi which is equal to sin x by cos x, which is equal to tan of x. So, what we see is that the tangent function is actually periodic with pi, because for any angle x, tangent of x plus pi is equal to tangent of x. And similarly, we can even show that tangent of x minus pi will be equal to tangent of x. Now, let us see what tangent of pi by 2 minus x is, since we had similar formulas for sine of pi by 2 minus x and cos of pi by 2 minus x. Now, if we treat this as y, then tan of y is sin y by cos y. So, therefore, this is sine of pi by 2 minus x upon cos of pi by 2 minus x. But from previous slides, we had shown that sine of pi by 2 minus x is equal to cos of x, and cos of pi by 2 minus x is equal to sine of x. So, tan of pi by 2 minus x is actually equal to the inverse of tan of x, which is usually called, which is actually a new function that we are defining here. It is actually called cotangent. So, it is written as cotangent, but we write it as cot in short. So, this is cot of x. So, tan of pi by 2 minus x is just the inverse of tan of x, which is also written as cot of x. And here in this class, in the third lecture today, we started with the expressions for cos of x plus y and cos of x minus y, and we derived lot of many different formulas for cos 2x, cos 3x, sin 2x, sin 3x, and we also discussed the tangent function. We formalized it as a trigonometric function, and we started with some simple expressions for tan of pi by 2 minus x. For example, here we show that it is equal to 1 upon tan x. We also drew the graph for tan x, and we saw that the tangent function is periodic with pi. In the next class, we are going to define the domain and range of this cotangent function, and then we are going to come back to the tangent function, and just like what we did for sine and cosine, we are going to see if we can derive formulas for the sum and for the tan of the sum and difference of angles. So, we are going to see if we can write tan of x plus y in terms of tan x and tan y, and similarly for tan x minus y, and also expressions for tan of 2x and tan of 3x in terms of tan of x. Thank you.